Last week in lecture, we watched a video that kind of gave us a little preview of reaction mechanisms. Most reactions occur in several steps. It's not just one thing that's happening, there's a series of steps. When we look at a chemical equation like this one, we just see the substances that are present at the beginning of the reaction and the substances that are present at the end of the reaction, the reactants and the products. But there can be actually some intermediate structures or compounds that are present. The reaction mechanism is the series of individual chemical steps. And so we can write a chemical reaction for each individual step. Those individual steps are called elementary steps, and those represent the exact things that are colliding in the reaction. So the reaction of hydrogen and iodine monochloride actually contains two steps. In the first step, a hydrogen molecule collides with the ICl, and that forms HI and HCl. Those are not the ultimate products. Then this HI that was formed collides with another ICl to form another HCl and I2. So those individual steps add up to the overall reaction. And so we can see how that works here. We can add these two equations. And we see that this HI was formed and then it was destroyed again. So that occurs on both sides, and so we can think of that as canceling out. And so H2 plus 2 ICl is going to form I2 plus 2 HCl. And if we go back to this, that's the overall reaction. So this HI here is called a reaction intermediate. It gets formed in one step and then gets used up in a later step. And so although that's present while the reaction is occurring, we are not necessarily aware of it. It wasn't one of the reactants, it's not one of the products that we see at the end. You guys have any questions about this yet? Yeah.
It doesn't matter which way the products end up, right? If I2 is first or...
Correct. If you switch the order of these, it's the same. Just like in math, 2 plus 3, 3 plus 2, same. Yeah. And thankfully the computer homework and stuff is smart enough to recognize that. Any other questions? So the reaction mechanism is a detailed description of the reaction at the molecular level. It's showing what individual collisions occur. Chemical kinetics help us determine the mechanism of the reaction. We can measure the kinetics of the overall reaction, and we can work backwards from that to write a mechanism that's consistent with those kinetics. That's really a starting point, though, because just because we can write a mechanism does not mean that that's the correct mechanism, but it's a place to start. So elementary steps are characterized by how many reactant particles are involved in the step. That's known as the molecularity, so how many molecules. A unimolecular step just involves one molecule. So here, a decomposition, we've got one molecule and it's just decomposing into one or more products. Bimolecular, you could have two molecules that are the same, reacting with each other to form products. Or also bimolecular is two different molecules colliding with each other to form products. Other molecularities are possible. Termolecular steps involve three particles colliding simultaneously. And so we talked about the need for the correct orientation and the enough energy in the collision. And so here, when you've got three things that have to collide simultaneously with enough energy and in the correct orientation, you can see that this is just not very common. So rate laws for the elementary steps can be deduced from their equations. And this is why I emphasized at the beginning that we cannot determine a rate law for a chemical equation just by looking at the chemical equation. Because the chemical equation that we see is almost never an elementary step. It does not describe exactly what's happening. So we can only find out what the rate law is through experiment. When we're looking at elementary steps, we can figure out the rate law from the equation. And because this is so convenient and easy, people want to do this for everything. And so I just want to emphasize, this is only elementary steps. An elementary step is where you're looking at exactly which two particles are colliding. So the molecularity for that elementary step is going to give us the overall order. So if we have one substance, a molecularity of 1, the rate law is going to be first order because there's one of these. Here we have a bimolecular reaction or elementary step. So we've got two A's colliding, and so here this is going to be a second order rate law, A squared. A plus B, we're going to get the rate is equal to the rate constant times A to the first power times B to the first power. And then here are examples for what that would look like with termolecular, which are very rare. So here we do see that the order is dependent on how many of these things are colliding. This is very appealing. It's straightforward and easy to understand, and therefore students want to do it all the time. I've mentioned this before, and I'll mention it again. It only works for elementary steps. Okay, only for elementary steps. So usually one of those steps in the mechanism is going to be a lot slower than the others, and that's called the rate determining step because it limits the overall rate of the reaction, and therefore it determines the rate law for the overall reaction. The example that we have here is traffic, right? So here we have 3 lanes, but they're doing some construction here, and so they have 2 of these lanes blocked off. We've got 3 lanes of traffic coming in, but they have to merge down to 1. This is going to be the rate limiting step. Cars getting past this point is going to determine how fast the overall traffic can proceed. Does that make sense? So here they're getting up, people, it doesn't matter how fast you come up here, it doesn't matter how fast you take off over there, you have to get through this, and that's going to limit the rate at which the cars can travel. So here is an example, NO2 plus CO. The experimentally determined rate law is rate equals rate constant times NO2 squared. If we look at this rate law and we look at that chemical equation, we say, well, how do you get that from the equation? You don't. You get it from experimentation. So, could this be a single-step reaction? It can't, because this does not match with this. If this was an elementary step, then this rate law would be rate constant times this concentration times that concentration. But it is not. This is a multi-step mechanism. So possible mechanisms, or a possible mechanism, is that 2 NO2 molecules collide and form NO3 and NO, and then this NO3 collides with CO to make another NO2 and CO2. This is a possible mechanism because when we add these together, we get the same overall reaction. Where do we come up with these possible mechanisms? Well, sometimes it's just like brainstorming. We're like, well, what could possibly be happening? I mean, we're really just kind of grasping at straws sometimes. So in this possible mechanism, this first step in which two NO2 molecules are colliding with each other, an elementary step, this is describing exactly what's happening. If this is the slow step, we can write a rate law for this step, right? The rate law for that step, the rate is going to equal a rate constant times NO2 squared. It's the concentration of this times the concentration of that. Well, this happens to match the actual experimentally determined rate law. The rate law for the second fast reaction, elementary step, could also be written, and that would be NO3 times CO. The rate determining step is the slow one, because this is what's slowing everything down. Once this step happens, the rest of it happens very quickly, right? And so this rate law is meaningless. There's no point in even trying to figure out what it is or what its rate constant is, because the first one is the one that limits the rate of the overall reaction. The first step is slower because it has a higher activation energy. So the reactants, these two combine to form this transition state, and it takes a fair amount of energy to do that. Then those, once it gets enough energy to get over this hump, then it can come to another transition state, but this is going to have a lower activation energy. You can kind of think of this as like a roller coaster or something, right? Once you get up the first big hill, you've got enough momentum that you can come down and you don't need any extra power to get up and over that one. You've got the momentum to do that, right? So once you get over the highest hill, you're good for the rest of it. So here the first step determines the overall rate, and that would predict that the rate law for that step is going to match the experimental data. Questions? No questions. That's okay. So there are conditions for a valid mechanism. The elementary steps in that mechanism have to add up to the overall reaction. And the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. So if these two conditions are true, then we have a valid or validated reaction mechanism. That does not mean that that is the correct mechanism. It just means that it's consistent with what we know. So mechanisms cannot be proven, only validated. There may be other mechanisms that also fulfill those conditions, and we would need more data to strengthen the validity of the proposed mechanism. determining mechanisms of chemical reactions is really difficult, because not only are we dealing with molecules that are too small to be seen, we're dealing with things that, those intermediates that appear and disappear, and so they can be very hard to detect. And so this is a challenging problem to determine the mechanism for a chemical reaction. Questions? So if a mechanism has a fast initial step, then the rate law that's predicted by the rate limiting step may have intermediate substances in it. And the rate law for that step with the intermediates cannot correspond to an experimental rate law. Why is that? Let's see if we can get, okay, so if we get back to this one, could this be the rate law for this equation? This has a substance in it that is not one of the reactants. This cannot possibly be the rate law for this chemical reaction. Okay, so a rate law cannot have intermediates in it for the experimental rate law. So what can we do with this? If the first step is fast, it can establish an equilibrium where the reactants are forming products, the products are decomposing back into reactants, and it establishes an equilibrium. There's two up here. So here's an example of H2 reacting with no. Here's our observed rate law. So here is a mechanism for that. We have two no reacting to form N2O2. This is a fast step. And then we have a slow step, and then another fast step. So let's show that condition 1 is met. Do these elementary steps add to the overall reaction? So, get out your pencil, and let's add these up and see if it works out. So before I start writing anything down here, I'm going to look for intermediates, things that are formed and then decompose and aren't going to show up in the end. Let's see here. So here we have N2O2 forming, and then here it's being destroyed. So those are going to cancel each other out. And then here I have N2O being formed and then destroyed. So I'm going to cancel that one out. And everything else is just on one side. So we've got two H2s and two no, and that makes two H2O plus N2. Do you see how this works, adding these equations together? We did some stuff like that in Chem 1A, but it might be kind of hidden back in the recesses of your brain. Anybody have any questions about that? So condition 1 is met. The elementary steps add up to equal the overall reaction. If they don't, the mechanism's just junk. Couldn't possibly be correct. So condition 2 is that the rate law predicted by the mechanism has to be consistent with the observed rate law. So what's the rate law predicted by this mechanism? And we're just showing the first two steps. We're not showing the last step. So it's the slow step. We can write a rate law for a slow elementary step. So that would be, get your pen out, rate equals rate constant. And so this would be the concentration of H2 times the concentration of N2O2. This is the rate law for this elementary step. This is not going to work as the overall rate law because it has an intermediate product in it, right? And that doesn't appear as one of the reactants. But because this first step is fast, we can assume that an equilibrium gets established. So we can express N2O2 in terms of the reactants for the overall equation. So looking at this equilibrium, when a reaction is in equilibrium, that means that the rate of the forward reaction is equal to the rate of the reverse reaction. So we can write a rate law for the forward reaction. So the rate for the forward reaction is going to equal a rate constant times NO squared. These are elementary steps. We can write rate laws just from the equation. Again, we can only do it because it's an elementary step. Don't get excited for other things. Does everybody see how I got that? We're looking at this first fast step. The forward rate is going to be related to twice the no concentration. We can also write a rate law for the reverse reaction. So the rate for the reverse reaction will equal a different rate constant times the concentration of the reactant for the reverse reaction, right? So this is going to be this going to that. Somebody has to have a question. So at equilibrium, the rate forward has to equal the rate back. So these have to be equal to each other. Oops. So the forward rate has to be equal to the reverse rate. Okay? So this is the rate law for this slow step, but we need to get rid of N2O2 in here. So we need to get rid of this, and what we can do is we can take this relationship and solve it for N2O2, and then substitute that in here, and that's how we can get rid of the intermediate concentration. So we can rearrange this. N2O2 is going to equal K forward times no squared divided by K reverse. You see that? Let's see. So this guy is equal to that. So we can substitute that in. I did not leave myself much space here, but we'll figure it out. So the rate is equal to the rate constant times the H2 concentration times Kf over Kr times no squared. This concentration is related to that concentration. I can derive an equation for that, and I can substitute this in here. So now I only have actual reactants in my rate law instead of some intermediates. This is a constant, and those are constants, and we don't really need to know what they are individually. Yeah?
KF and KR are still different, though, right?
KF and KR are still different, and they're different than this K, but they're all constants. So what we're going to do is we're going to lump them together. So we're going to take all three of those, and we're going to say, call it K prime if you want to, is equal to that original K times KF over KR. So I'll put it down here. The rate is equal to a constant times H2 times no squared. A question involving doing this will show up on the exam, so this is not one of the things that you can just ignore. Any questions? Yeah.
I don't fully understand what it means when the reaction's in equilibrium.
Okay. So what does it mean when the reaction is in equilibrium? So this is something that we really didn't talk much about in Chem 1A. It was in Chem 3A, but that was probably a long, long time ago. And we will talk way more about equilibrium later in this semester. For now, what we need to understand is reactions do not always just go in one direction. That happened a lot in Chem 1A, but we were kind of simplifying things. Most reactions, well, a lot of reactions can go in both directions. So here, two NOs can combine to form N2O2, but then some of those N2O2s are going to fall apart to form two NOs again. And so it's going to go back and forth. It's called a dynamic equilibrium because both reactions are happening at the same time. It's a little bit like traffic on 99. There's cars going north and there's cars going south at the same time. And depending on what's going on, you may have a net flow of cars towards Fresno or away from Fresno, right? But if you get an equilibrium where you have the same number of cars at each end, then the number of people going north and the number of people going south are equal, even though they are not the same people. Another analogy would be an airport. So you have people arriving on airplanes and you have people departing on airplanes. And unless something gets, screwed up with the system, you'd have the same rough number of people in the airport at any given time during the day, right? Because you have people coming and then you have other people leaving. And so overall, the number of people in the airport is roughly the same, but it's not the same people, right? And so that's an example of a dynamic equilibrium. Does that make sense? Yeah, great question. So, I labeled these Kf and Kr, and here's K, and then I call this K prime because we shouldn't just say, well, okay, well, that's just equal to K, because it's not. But all of these three things are really meaningless constants. They have no significance, no physical significance. But they are constants, and so we're just going to lump them all together into one, and then this would be the rate constant for the rate law. Anybody else have questions? Okay. So here is an example problem where we need to do this. Okay, so ozone naturally decomposes to oxygen by this reaction, and the experimentally determined rate law for this reaction is given here. Show that this proposed mechanism is consistent with the experimentally observed rate law. So here's our overall reaction. Here's the rate law for that reaction. And here we have a mechanism. So we need to show two things to say that this observed rate law is valid and that the mechanism is valid, right? The first thing is that the steps in the mechanism have to add up to the overall reaction. And that's the easiest part, so let's just check that first. We'll take these two steps and add them together. So here's an oxygen atom and an oxygen atom. Those are going to cancel each other out. And what we've got left is 2 moles of ozone and 3 moles of oxygen. Does this mechanism pass the first test? Yeah, it does. If we add these together, we get the overall reaction. So the next step is that we have to show that this rate law is consistent with what we would get from this one, from the mechanism. So in the mechanism, here we have a fast first step and a slow second step. So whatever the slow step is, we're going to write a rate law for that. These are elementary steps, and so we can do it right from the equation. So the rate law for this slow step is going to be equal some rate constant times the concentration of O3 times the concentration of O. O3, there's only one of those, and O, there's one of those, and so these are first order for each. Everybody see how I did that one? And again, this is nice and easy. You can't do it for just any old equation. It has to be an elementary step. This is not an elementary step, so we can't just do that. Well, does this match that one? Well, no, because this has O2 in it and this has O. This is not a good overall rate law because it has an intermediate product in it. It does not have only the reactants, or in this case, the products. The things in the rate law have to be present as reactants and products. So we're going to do what we did earlier. We're going to look at this first fast equation, and it forms an equilibrium. It's fair to assume that. And so the forward rate for that would be equal to the forward rate constant times the ozone concentration, right? That's going forward. And the reverse rate is going to be the reverse rate constant. Now we're going from the right to the left, And so this will be the concentration of O2 times the concentration of O. So everybody okay with where this came from? Any questions about that? The definition of equilibrium is that the forward rate equals the reverse rate. So I'm going to move up to the top here because it's getting crowded down there. So the forward rate is Kf times O3, and the reverse rate is Kr times O2 times O. This is the rate law for the slow step, and this is our starting point. We're trying to get to this one and show that this is valid. This is not okay because it's got O in it, and O does not show up as a reactant or a product. It's an intermediate. So there's no way we can know its concentration. So we're going to take this forward equals reverse thing and solve it for O so that we can substitute that in here and make it go away. Right, so we want to find out what O is in terms of the other things. So the concentration of oxygen is going to equal the forward rate constant times the concentration of ozone divided by the reverse rate constant times the concentration of oxygen. So I took this equation and I solved for O, divided both sides by KrO2. Now I'm going to take this piece here and I'm going to substitute it in for O. So I've got my rate law from the slow step. And for O, I'm going to put in what I found O to be equal to. So I'm taking this one down here that I got from the slow step, and I'm subbing in for the O because I can't have O in there. And I get that relationship by looking at an equilibrium forming in the fast step. So now what we're going to do is we're just going to collect all of the constants into one constant. So this is going to equal a constant, I'm just going to call it K prime, and O3, and O3 divided by O2. So I took these K's and I lumped them all together and called them K prime. Okay? Now, this does not look exactly like that, but it is actually the same thing. So what we have here is a rate constant, so we've got a K, and we have O3 times O3, so that's O3 squared, and 1 over O2 is O2 to the minus 1. So this is O2 to the minus 1. Yeah.
Is there a reason you couldn't just solve for O over O3, or could you solve for either one and still get the same answer?
Is there a reason I solved for O here, for this one?
Yeah, like the first rate you wrote rate is equal to K O3 at the bottom.
Mm-hmm.
So could you just solve for O3 instead
No. So if I solved this for O3 and substituted that in here, I'm still going to have oxygen atoms as one of the substances, and that's what we're trying to get rid of. Yeah, that's a good question. You could take that and go a couple more steps with algebra and make it come out to be the same thing. Yeah, it's not that it's not a true statement, but it's not useful. Yeah. So, to show that the mechanism is consistent, we first have to show that the mechanism steps add up to the overall equation, which they did. And then we take the rate law for the slow step and we substitute in here to get rid of any intermediates. And we came up with a rate law that matches the experimentally determined rate law. So that tells us that this mechanism could possibly be the correct mechanism. It fits. Doesn't prove that it's the right mechanism, because you could write other ones that would work out as well. But it's possible. Any questions? Predict the overall reaction and rate law that results from the following two-step mechanism. Well, how do we get the overall reaction? We add the steps together, right? So if we add these steps together, let's see, there's A2 that is formed and decomposed. So we want to get rid of any intermediates, which is kind of like getting rid of spectator ions. So we have 2A plus B is going to make A2B. So that's the overall reaction. Any questions about that? Predict the rate law. Well, the one that we were just looking at had a fast first step and a slow second step. This one has a slow first step. When the first step is slow, it's never going to have intermediates in the description of the rate law. So here, if we look at the rate law for this first step, the rate law is a rate constant times what? A squared. Well, A is a reactant. If we have something with A2 in it, that can't possibly be the rate law for the reaction, right? But when we have a slow first step, we can just use the rate law for the first elementary step, and that should work for the overall reaction. So if the first step is slow, it's easy. If the second step or the third step is slow, if the first one's fast, then we've got a little more work to do. So the overall rate law is predicted to be the rate equals rate constant times the concentration of A squared. Any questions?